understanding of how the hardware work. So how really your laptop or how really your computer or your mobile phone works, right? So with that in mind, I have here. I don't want to share my screen right away, just because I want to show you a real hardware, and then from there I want to build up concepts which will be essential for you to understand at a much broader level. Okay, so here I have. So I don't know whether you can clearly see this, but let me try my best. So what I have here is an old laptop which I broke apart and then disassembled it. So what you're seeing here is the motherboard essentially. Okay. Um, so I'm going to talk about very few some of the most important components on this board, which will lay the foundation for us to really understand and appreciate what an operating system is and how it does what it does. Okay, so uh, let me know if you can. If I think it's focused properly, so let me know if it is not. So again, you can see on the sides the familiar connectors that you see for any laptop. So this is a very tiny laptop, which is almost like 10 years old. So it's not working anymore. So that's why I disassembled it. So all you can see is these ports, which you can probably recognize. Unfortunately, these days, nobody is actually using desktops, if I'm not wrong, at least the majority of the people. So you never get to see how your computer look like, right? So this is your chance to take a look at it. So the sides of it, you're very much familiar with it because it's exposed outside. And now the most important and the crucial part here is sitting behind this, the cooler, basically. So behind this is what we have, the CPU, and then this is the RAM. I'm going to take this cooler aside for a second, so that you can clearly see how the CPU actually look like. Unfortunately, it has the thermal paste, which we apply to keep the CPU cool. So the top one that you're seeing here is the CPU. This, I believe, is Core i3, sometime back, almost like a decade back. So this is the central processing unit, which does the execution and all. And just beside it, you see something called as PCH. PCH stands for Platform Control Hub or something like that. So the main responsibility of that is to help you. This is the one. This is the chip that actually provides all the peripherals. So all of these peripherals are not actually connected directly to your CPU, but instead they are connected to the PCH. Okay, this is pretty standard. Again, this is all dictated by Intel or AMD. So what they do is when they are building new chips, they also give the entire specification for how the motherboard should look like. When I say motherboard should look like, it's not about how these components are laid out, but more of how the communication should happen between the components. Okay. Again, this is also not very much interest to us, at least for today's session. We are mostly interested on this part, which is the CPU. And just beside it, you see something called as RAM, which you might be very familiar with. Let me try to open it. I don't know whether I can. But basically what we have here is like this is removable, and then you can replace it with different RAM sticks if you want. But what we have here is basically we have two RAM slots here. This is one RAM slot which is already populated, and this is one RAM slot. Probably I removed it, so you don't see another RAM slot here. Okay, and then so when we say RAM is closer to CPU, what we mean by this is this. So CPU sits right. I mean, RAM basically sits right next to the CPU. Okay. Now, the other important part, which is currently not connected, is here. So this is the hard disk. I don't know whether you saw it. This is the SSD, solid state drive. Now, what we do is this goes right next to the connector here, something like this, like this. Okay. So if you look at the hierarchy here, so we have the hard disk, and we have the RAM, and we have the CPU, the most important components that uh, any system would need, right? So unfortunately, the connector is very flimsy here, so I don't know whether it can hold longer. But let's quickly move around the components. So this is the connector for this laptop. This is the old Lenovo laptops used to look like this, the yellow circular connector. So once you power this on, so once you connect the adapter, the battery adapter to this, that's when the board will get the power, and that's when we say we actually. The funny thing is, even before you switch on your computer, it does get the power. So the board will already get the enough power, but there is a reset pin. Again, it depends upon which device, which board you're talking about. So the what is the reset pin differs between board to board. So let's not go there. Assuming when you press the button on the computer or in the laptop, what it actually is doing is it's basically triggering the reset pin. So once you press the reset pin, that's when the actual power gets distributed to your CPU. Okay. Now, um, once the CPU is turned on, the first thing that happens is basically CPU has a hard-coded location where it goes and start executing code. Okay. Now, again, I'm not talking about the hard disk yet. I'm not talking about the RAM yet. I'm just right now, my control is still in the CPU, and it didn't start executing any code right now. Okay. Right now, we just press the reset button. Now, assuming the CPU just started executing it, as I said, the CPU will have a fixed location where it will go and execute. When I mean what I mean by fixed location is uh, basically within the RAM, there will be a fixed location where it will go and start executing code from there without even thinking about what's there in it, or whether it's an OS or whether it's something else. It doesn't care. All it does is it goes there and then it fetches those instructions and then it starts executing it. Okay. Now, again, many people think that when the CPU is turned on, your OS gets executed first. No, that's not true. Basically, I what happens is every motherboard, okay, every motherboard will have a special chip. I don't know whether you can see it. Usually, it look like this with an 8-pin chip, right above the this battery. Okay, so this chip is called Spinar. It's basically a tiny memory chip which actually holds your BIOS. So that's what we call firmware. So the word firmware looks so fancy, but at the end of the day, it's basically a piece of software. Okay. Now, um, like I said before, when you turn on the CPU, the first instruction that gets executed is from this tiny chip. So this is basically a small, tiny memory which contains unmodifiable code. So that's why whenever you buy a laptop or whenever you buy your desktop, you tend to format it, you tend to upgrade your OS, but you never ever, very rarely, at least as a users, you never update your BIOS. Okay. uh, what I mean by that is technicians can do it. So basically you can put some connectors to it and then you can update this BIOS as well, but we are not going there right now. So just coming back, once you turn on the CPU, the BIOS from this Spinar chip gets executed. The purpose of it is basically to do some basic initialization of the board. And then what I mean by basic initialization is basically to initialize the RAM and also to initialize any external peripherals. Not all of them, very basic peripherals like the hard disk and things like that. Once that is done, the BIOS will hand over control to the operating system. There is a well-defined mechanism in which that happens. Let's not again go there, because that itself will take a session on its own. But the idea is, when you format or when you install an OS on your hard disk, what happens is, Windows or Linux, it doesn't matter. Both of them, they install their respective files, but also they install a specific file called bootx64.efi. It's an EFI application. It's a special binary, so it will be present in a fixed location. It will be in a special partition within that hard drive, and then within that special partition there will be in a fixed location. So the name of the file is called bootx64.efi. Now, every modern BIOS know how to reach to that file and then start executing the contents of that file. Okay, there's a huge contract of how to do it and how that execution happens. But the point here is, you get to that, so that this is the first time we are actually executing something from the hard disk, which gets connected here. Okay, now again, at this point we have not yet launched the operating system. We haven't executed anything on the OS side, essentially. So again, in this talk I'm going to concentrate more on Windows, but the concepts equally apply to Linux as well. It just so happens that I have been using Windows for quite some time, and also there are some very good tools which we are going to see today to leverage and also understand the general OS concepts. Okay, so coming back, right now we turned on the CPU. The CPU read the BIOS from that special tiny chip, and then it initialized that code which is in that tiny chip, initialized the basic peripherals, and then the BIOS also, the code within the BIOS also is able to look for that special file which I mentioned as bootx64.efi. Again, I'm talking about x64 platforms here. If you talk about ARM64, the file name will be different. Mostly we all of you have like x64 laptops, so that's pretty familiar. So the idea of that file is called, the reason why the file is so important is because that file is what we call the bootloader. So the reason why we call that as a bootloader is because that's the one which will load your operating system, be it Windows or be it Linux. Okay, so I'll talk about what will happen when the OS gets loaded and things like that. But primarily, if you look at this hardware, one thing which you should be very familiar with is the CPU. It doesn't care what OS you're running. Okay, it really doesn't care what content is there in the RAM. Okay, all it does is basically read bytes from the memory, the RAM, and then start executing it. And as part of its execution, when I say execution, what I mean is basically, if you read a byte or if you read a couple of bytes or instructions as we call it, what happens is those instructions, essentially those instructions are nothing but the x86 instruction set, like the assembly language instructions. So those gets executed, and then any results, let's say it read a few bytes from location 1000. Okay, so those bytes happen to be when the CPU gets decoded, those bytes happen to be move x comma 10, something like that, or move ex comma 10, something like that. So what it is actually doing is, when it is executing that instruction, any data that it is manipulating will be returned back to the RAM. Okay, now it so happens that sometimes the content that you write back to the RAM will eventually go back to the peripherals. In this case happens to be the hard drive. Okay, again, we are not going into the nitty-gritty details of how this entire thing happens, The idea of this session is to give you a high level overview of how things work, and give you a chance to drill down as needed. Okay, so one thing that I'm keep repeating myself here is CPU is so naive. It doesn't know when to stop. It doesn't know when to transfer control and things like that. All it does is it's so blind in the sense that it will keep executing instruction after instruction after instruction. Okay, now assuming there is no operating system, let's rewind back to, let's say, 30-40 years, right? Now what used to happen is, in those days, like the memory used to have only one piece of code, and we don't have the concept of a process or a thread or a memory or a process or thread or things like that. We do have the concept of memory though. So the code in that RAM gets executed, and then the CPU gets halted. CPU is basically stopped. That's how it used to be. Now, in order to make the hardware more, the utilization of the hardware more efficient, or make it more usable, slowly people started thinking about to manage or to create more better ways to orchestrate what the CPU does. That's where the idea of operating system came in. So what operating system essentially does is it basically instructs the CPU what it is supposed to do. Okay. Now again, I'm keeping it at a very high level, because when I say operating system will instruct the CPU to execute something, you have to think yourself, um, if operating system is actually instructing the CPU, where exactly is the operating system even executing, right? Does it make sense? So I'll talk about those details, but primarily, like I said, when you install your OS, that goes into the hard disk. Okay, and then that hard disk that operating system gets loaded by the bootloader, which I talked about. Now the loaded operating system will be sitting in the RAM. Okay, now again, naively, what the CPU does is it start executing the operating system code. Okay, again, at this point in time, we don't have the concept of a process, we don't have the concept of a thread. Okay, it's a lump of code that is sitting in the RAM, which is being executed by the CPU. This is what we call phase zero initialization of the OS, at least in Windows. So what that does is, in phase zero, we don't have the concept of process, we don't have the concept of a thread, we don't have the concept of a user login or anything like that. It's basically a piece of code, essentially the operating system, which is being executed by the CPU. Now the crucial parts within the operating system, which helps the system to eventually become like a multi-user environment, there are a couple of components within the operating system which are very essential to make the system usable by multiple users. Now in phase zero, the operating system basically, like I said, is a lump of code sitting in the RAM. Now one other crucial thing that is absolutely important for the operating system to work is called a timer interrupt. So every like 10 microseconds or something like that, what happens is there is a clock within the PCH which will interrupt the CPU. So if CPU blindly starts executing the code, then it becomes very hard for the OS to decide, like when let me repeat myself. So if the OS starts executing the code of the if the CPU starts executing the code of the OS, um, there is no way you can decide what program to execute next, or when to stop the currently executing program, right? So every now and then, in fact, every few microseconds, the CPU gets interrupted. Okay, there's a timer signal that gets sent from PCH to CPU, which will interrupt the CPU at every, let's say, 10 microseconds. Now, whenever the CPU gets the timer interrupt, which is very important signal, what that does is it will execute a special function within the OS code. We call that a timer interrupt routine. The idea of that is it's almost like giving the OS a chance to decide what needs to be executed next. Okay, let me repeat this. I don't think I have conveyed the idea of how these things are working. Number one, we have OS here, which got loaded, and let's assume there is a second program that got loaded. Let's say BT or Notepad or whatever. Again, right now Notepad is too high level for us, but let's assume there is a second program that got loaded. Okay, CPU can only execute one program at a time, right? So either it could be executing the operating system or it could be executing the program. Okay, now because of the help of the timer interrupt that I just talked about, so every 10 microseconds the timer interrupt gets fired to the CPU, and CPU, what it does is, even though it is executing your program, it goes back, it gives the control back to the OS. When I say giving back the control, what I mean is it essentially executes the timer interrupt routine within the OS code. Does it make sense? Now that timer interrupt code, what it does is it will determine what is the just prior executing task. In this case, it's program 2. Now OS scheduler will decide whether to continue executing program 2 or to basically give control to, let's say, program 3. Does it make sense? So scheduler is very important within any OS, which will basically perform these switching of execution from one program to another program. This is all done with the help of this timer interrupt. So no matter what program is getting executed on the CPU at any given point in time, in the next time lapse, the 10 microsecond time lapse, operating system will always gets the control back, and basically operating system will get a chance to decide what other program to execute next. This is at a very high level what a scheduler does. Without the timer interrupt, there is no concept of scheduling, because uh, it's very obvious, because once the CPU starts executing program 2 without interrupting the CPU, uh, even the OS cannot get a chance to execute its own code to decide what other program to give control. Does it make sense? Okay, so again, when I say OS, what I mean is, like I said, there is no concept of process right now at this point. Now, once everything is initialized and everything is, basic infrastructure is laid out by the OS, then OS, what it does is it will basically create the concept of process, without which we as a user will not be able to will not be able to utilize the system that we have. Okay, so I'll go over the details of what a process is and how a process will look like, but the most important and the most fundamental point, like I said just now, is no matter what the CPU is doing, for every 10 microseconds the OS will definitely get the control back, so that it can decide what other next program to execute. Okay, this is a very important point to remember in order to make sense of other concepts that I'm going to talk now. Many people think that when we say OS, um, it's not a process on its own. Okay, it's not something magical, or it's not something that gets executed some randomly or anything like that. So it's a well defined piece of code. I'll show you what it actually look like. uh, what it does is the sole purpose of the OS is to not only manage the resources that are there on the on your platform, but also, like I said, execute the give control to the basically multitasking between the programs. Okay, so I'll keep this aside, and then again, one thing which I wanted to show you is there is this display connector here. So this is where your laptop panel gets connected. Again, this comes as a peripheral to this entire board. You don't need any of this. If I connect this board, the CPU will work. Okay, I'll keep this aside, and then I'll start sharing my screen to actually look at some of these concepts what I just talked about. So I didn't get time to actually prepare a lot of slides for today's session. Also, just because this session will be a much better if we make it more hands-on. So I'll go over these slides, but primarily the agenda for today's session is I wanted to briefly talk about the hardware, which we have done just now. And then I'm going to use this tool called System Informer. Earlier, it used to be called as Process Hacker, which is a free tool again. This is the tool that we are going to use in and out to explain and understand some of these concepts, okay, at a very high level. Unfortunately, the problem with the textbooks that we use for undergraduate courses is they almost talk too much about the theory, but very less on the practical sides. So in fact, some of the stuff they talk about is almost outdated, and it's not very relevant in the context of a normal real operating system. So that's why I wanted to put a lot of emphasis on this tool, because it helps you clarify so many of the concepts that you will learn. Okay, so I'll talk about the installation and all of that, and then I'll also spend some time on how the interface will look like, and then followed by that I'll actually help you understand on the real OS concepts. Okay, now I'll go here later, but before that, let's jump into the tool itself. Okay, so all you have to do is System Informer in Google, and then what? Oops, give me a second. Looks like the site is out, but let's try the GitHub. Let's come back to this later, maybe. All you have to do is search System Informer in Google, and you will be able to download the installer for it. Now, the installation is pretty familiar. You just have to click next, and then the installation should happen. And if you see on my taskbar to the lower corner, what you have is the tool itself. Again, I have changed the resolution, so I hope you can see the screen. If not, please let me know right now. Okay, I'm assuming the screen is visible to you all, and so this is how it will look like. This is the tool that I'm going to walk you through to understand the concepts. Okay, first and foremost is basically whenever you take a laptop or a system, you basically want to know the system configuration, right? So the first thing that you come after installing this tool is you just click this system information on the top of the toolbar. Okay, now it will look something like this. Okay, the first one is CPU, memory, some other stuff. We don't care. The most important thing is CPU. So if I click the CPU, you see something like this. Okay, now this CPU is almost like you can see the name of the CPU, which happens to be Intel Core i9, and then looking at this itself, it's a lot of information to take in. But this is basically the utilization graph that is what you are seeing here. So the red thing is what we see, the whichever process is basically taking. You can see that red basically indicates the kernel mode time, and green indicates user mode time. Okay. Now, this is not so super interesting, but when I click this checkbox, show one graph per CPU, you will see something like this. What you're looking at here is I happen to have this CPU which has almost like 24 cores in it. Okay. So you can, so the chip that I have showed you, this one, we call this a die. This is one die. Okay. This die internally can contain multiple CPUs within it. Okay. So also, yeah. So in this case, it happens to in my desktop machine happens to have like 24 cores within it. So 24 execution units that are there on that on my specific CPU. Now, the beauty about this is you can clearly see which core is most active or which core is not so active. So if you look at here, this core is doing nothing. Okay, this core is doing something. Again, this core is doing something. Okay, so just by looking at this screen, you can say whether, sorry, let me turn off my, oh, it's still, in fact, I can use process hacker to terminate it. Let me see. Okay, so just by looking at the graph itself, you can see whether your system is like almost heavily used or not so heavily used. So this is one very good metric to understand. Then comes the memory. Okay, so I can clearly see how much memory is installed here, memory as in the RAM, and then some more statistics here. Ignore the top part. You have to look at the physical, which will tell me like currently I'm almost using 13 GB out of my 32 GB. All of the processes are taking almost like 13 GB of RAM out of my 32 GB of RAM. And then you can see this IO section, which will talk about are there any writes that are happening heavily? Are there any is there any download that is happening? When generally when you download something, like basically it has to be written to the hard drive. So that's when you would see the IO activity happening here. Okay, and I think I do not have a discrete GPU, so I don't have a special separate graphic card. So this one is part of the CPU itself. So that's why you're not seeing anything like NVIDIA or AMD, anything like that here. You are basically seeing an integrated graphic card. So apparently, even the integrated graphic card is really powerful. So it has got these many individual cores. If you happen to have a high-end NVIDIA graphic card, then you would probably see much more independent nodes here. Okay, so this is how basically you can, at a high level, you can get a sense of what your system is and what its configuration is, and whether it's busy or not, whether it's consuming a lot of memory or not, just by looking at these graphs. Again, we don't have to care too much about these numbers here. All we have to care is if the memory is going high, by looking at the graph, we can clearly see something is happening or some program, or we'll figure out which program is taking and things like that. But just by looking at this, we can get a good sense of what your system is doing. Okay, now again, okay, let me minimize bunch of stuff here so that you'll get a sense of what it will look like. So the most important section of this this tool is this processes tab, which will list out all the processes that are running in your system. So even before I show what the processes are doing here, I just want to take a minute to help you understand what a process even mean, right? So again, let's not go to any bookish definitions, because they are always confusing and they don't really make any sense. So in my mind, when I say process, what I think is basically, process is basically a collection of resources for us to exercise something. Okay, so when I say resources, what I mean by that is, you need a RAM, you need some memory to store your program, and then you need some CPU to execute the code within that memory. Okay, so essentially process is basically an abstraction to collect, to talk about these related resources. Okay, so when I launched Notepad process, what I mean by that is, I'm basically bringing up pulling all the files required for Notepad to run successfully. When I say pulling, what I mean is, like, you have some set of files for Notepad lying around in your hard disk. So what we do is, we bring those files to RAM in memory, and then essentially we try to execute those loaded binaries. So we cannot talk these individually, like 10 files from hard disk, or like 10 MB of RAM is utilized to run Notepad, things like that. We won't be able to talk individually. So that's why operating system designers have introduced this concept of a process. So when we say process, what we mean is, we are trying to achieve something, or we are trying to exercise or execute something based upon a bunch of resources. Here, like I said, you pick up some files for Notepad, and then you load them into RAM, which means you take some part of the RAM, some memory, and then you give control to CPU to start executing that code. Okay, so collectively we call this as a process. So process is basically an entity which contains these resources, which the CPU can execute sequentially. Okay, so a system can have like multiple processes. One process can create another process and things like that. Okay, now, like I said, in phase 0 of when the OS gets started, it will not have the concept of process, because we are very early in the booting process. So there is no such concept as a process. Now, once the infrastructure, all the data structures or whatever, in order for the operating system itself to work, is laid out, that's when phase 0 initialization will be done, and then we move to phase 1. In phase 1, the operating system will creates its first process. Okay, now, um, uh, up until that point, even though the CPU is executing the OS, we don't say it's actually executing some process, because there is no such concept as a process at that point in time. Now, in phase 1, the first process that gets created is called as system process. That's what you're seeing here. Okay, this is the first system process. If you look at the tooltip, you would see it says anti-kernel and system. Okay, now, for historical reasons, which I'm not very super familiar with, is a within Windows, not with every operating system, but just within Windows, the first operating system process will get a process ID of 4. So this is what you see here. The processes will not be managed using their name. Instead, they are managed by their ID. We call it as process ID, PID for short. So that's what you're seeing it. So every system process, which nothing but the operating system itself, to be accurate enough, but this gets done in phase 1, not in phase 0. So phase 1, operating system introduced the concept of process, and it will give process number 4 to itself. Okay, so uh, once you go into the details of how it will look like, you will understand it, but at a high level, this is what it does. Now, you can ignore all of the things that are coming beneath it. We call it as child process, because this is the parent process and this is the child process. So this is basically the Windows operating system itself. Now, in this tool, what we can do is, you can right click on this the top bar, and then you can select choose columns, and then you can add command line. Okay. When you do that, just give me a second. Yeah. You can actually see where the binary is coming and things like that. Unfortunately, even for system, it should show. I don't know why it is not showing, but let's see. So ideally, this is where it is actually coming from. When we say Windows operating system, what we really mean by is this NTOS kernel, NTOS and kernel.exe. It lives in system32. This is the core of the Windows operating system. In fact, when we say operating system, this is what we are referring to. Okay, you cannot run it by yourself, even though its extension is .exe. Again, like I said, it's basically a lump of code that will be read by the bootloader and will be loaded into the memory. Okay, so now, so like I said, this is process ID 4, and then once that is done, this will, as time progresses, this will eventually launch some other supporting processes. Okay, that's what you're seeing here. Under Win init, you will see bunch of services and bunch of processes that gets launched. Okay, again, at this point in time, the user didn't logged in. He didn't log in. So even for you to open your laptop and to get your login screen, this whole stuff has to happen, without which you will not be able to get to your login screen. Okay, that's why if you see the username, it says NT authority system. What that means is this process is basically created by the operating system itself. Okay, let me minimize that, and then if you see something below this, not this one, anything below this, essentially what you see is you will see my name. Okay, these processes are actually created after I logged in. Does it make sense? So every process will have a user associated with it. Essentially, the up until the login screen, there is no user. So all of the required system level processes gets created by the operating system itself. Okay, now let's try to look at one process. That way we will get a sense of okay, even before I go there, I just want to okay, let's straight away jump into the details of a process, how the process will look like. That will give you more insights into what we mean by a process in greater detail. Okay, so just look at, I just double click this process Win init. You could open anything. You can right click and then you can go to its properties. So what you're seeing here is absolutely you need the program itself, right? Without which operating system can't even create the process. Like I said, assuming you want to launch Notepad, right? You basically need notepad.exe, without which you won't be able to create Notepad itself, Notepad process itself. So the most basic thing is you need the image, you need the file which contains the code for your program, essentially. Okay, so here it so happens that WinInit is coming from system32. So this is the one of the most important part. Now, sometimes when you're launching process, the process will take some command line arguments. Okay, apparently this is not taking any arguments, so that's why you're not seeing anything. But let me show you. Let me show you this. So if you see this, I double clicked PowerPoint. So if you see this again, the actual program for PowerPoint is coming from this location. So by looking at this, you know what process is, where the program is coming from. One thing I forgot to tell you is Windows by default comes with something called as Task Manager, but I highly discourage not to use it because it's good, but it doesn't expose you all these details, which is very important in my opinion. So when you install Process System Informer, go to its options and then make sure you replace Task Manager with System Informer. You can just click a button here, which will, whenever you try to launch process Task Manager by right clicking Task Manager, instead of launching Task Manager, it will launch System Informer. Okay, that will save some time whenever you want to use this. Okay, so coming back, so if I happen to run, if I double click PowerPoint, like I said, you will know clearly where the program is coming from. Okay, in fact, you can click these buttons to open the location in Explorer. But the most important thing is you can actually see what is the command line arguments that are passed to this program. Okay, not every program needs it, but if a program, let's say in our first session we did something like code space folder name to launch the directory in VS Code. Basically that folder name is the command line argument for code. Okay, so in fact we can see that here. So let me show you. So I have the command prompt here. Let's say we go to let's say I want to open some file. Watch what happens here. So again, this terminal corresponds to this Windows terminal. Okay, now the moment when I type notepad space something, you get the notepad launched. But if you look at the the System Informer, you will see notepad got launched. Now the notepad, if you look at it, you will see unfortunately they are making Windows more complicated day by day, so I want to make it much more easier for you to explain. Okay, I'll use Notepad 2, which is much easier to explain what we are trying to do here. So look at this. I tried to launch Notepad 2, which is another program. So if you double click that, you can clearly see where the program came from and also what the command line argument that I passed. In fact, what I passed is vimlib. I'm trying to just open a file which is named vimlib.pc.in. That's what we are seeing here. So just by looking at it, we can say how a process got launched. Okay, so let's say I have a Chrome here. Okay, so if you double click it, apparently the original Chrome binary didn't have any command line arguments, but because I don't launch it from command prompt. Now, if you look at any of its subprocesses, you will see bunch of command line arguments that are passed to it. In fact, like there are like almost like 12 command, almost like 11 command line arguments that are passed to it. Okay, so this is one way to look at how the programs got launched and things like that. And the important thing is like you can also see when it got started and also what is its current directory. Okay, some details related to it. And one very important information, at least in this screen, which is very useful, is this verified thing. Let's say you downloaded some random binary off of internet and then you double clicked it. Now, if you go to Process Explorer, I keep getting the name Process Hacker because they very recently renamed it to System Informer, whatever. So if you open that binary which you downloaded from internet to see what it looked like, if it is coming from a reputed sources, you will see this verified thing. If it is not coming from a reputed sources, you will see unverified. So that's a sign for you to be suspicious, whether you are running some malicious program or things like that. So most of the Windows binaries, and in fact every Windows binaries and any binaries that are coming from well-known publishers will have this verified thing. So you can look at that and you can decide whether to trust it or not. Then there are the statistics tab. I'm not going to go there. And there is this performance tab, which is often kind of very useful. Let's say you have written a program and then it is consuming a lot of CPU. You can just double click that program's code, and then program's process in System Informer, and you can come here and you can see how the process is, the CPU usage is getting elevated. I have a example to show you, and with that you can see how the process gets elevated. But this is basically the window where you come and see to inspect that. Now, I don't know whether you guys observed it, but every time a new process gets created or launched by other processes in the system, you will see a green highlighting here. So let me show you that. See, the red highlighting you just saw here is basically when the process is getting terminated. If a new process is getting created, you would see it in, for a split second, you will see it in a green color. So let me launch another notepad, another notepad too. Do you see that? There is this green color that you see. If I try to close it, you will see a red thing. It's basically an for us to give us a glimpse of when the process is created and which process is getting terminated. Now, I'll go back to threads later, tokens later, and then modules is important. Like I said, even though we think that we are launching notepad.exe, that requires a lot of support DLLs or support binaries, without which you will not get the UI or you will not get any functionality. So every process, like I said, even though it starts with one binary, instead the process will have like a bunch of files associated with it. So that's why I call process is sort of an abstraction. It's just a concept to talk about all of these related things, related resources. Okay, so modules will show you what other binaries are loaded into this process to launch that notepad program. Okay, similarly, there is this memory. Okay, so now this memory will give you a glance of how much memory the process is actually consuming. Okay, so you can, again, we're not going to go into the details of it, but at a high level, the point I'm trying to make here is just by looking at this window, you can get a sense of what a process is, what a process even contain, and how does it manages resources and things like that. And the other thing is there is this environment tab. In every session of ours, like be it VS Code installation or Git installation or whatever, in fact, whenever you install Java or Python or whatever, you tend to set the path environment variable. The reason why we do that is because subsequently, whenever you want to launch that binary, that program, let's say Java or Python, you don't want to type the entire name of the program, like C:/program file/ wherever the Python is installed and things like that. Reason for that is you update the environment variable called path. So you try to add let's say Java or Python directory to the environment. Now, when you do that, what is actually happening here is from then on, whenever you launch a process, every process will have this information of where to look for binaries. That's why when you set the path, when you install Java or Python, all you have to do is launch a new command prompt to take advantage of it. So when you launch a new command prompt, that new command prompt will get the updated environment variable. Okay, so again, what I'm trying to explain here is the concept of environment is basically baked into the process itself. So every process has the concept of environment. So all the variables that you define in your environment variables essentially gets reflected in your process like this. So there are user environment variables, there are system environment variables like that. So again, how you utilize these environment variables is again depends on the program that you are running. But when I say process, it also contains this additional piece of information called environments. Okay, now In fact, let me show you that so that it makes a lot more sense. So we come here, we go to environment variables, we double click this path, and then we try to add, if you install Java, you try to add the Java installation path here. When I do that, what I'm actually doing is basically from that point on, whenever I create a new process, that process environment block will contain the new directory that you added. So this is our way of telling Windows that I want my environment to be updated for subsequent processes. By doing so, every process will get the updated path, and you don't need to type the entire path to that binary, be it Java compiler or be it Python. Okay, so this is one thing, and the other thing is handles. Again, this is a Windows specific thing, but in Linux we call these file descriptors, FDs, but Windows we call them as handles. Essentially, what we care about here is you don't need to care about a bunch of other things, but all you can care about is the files type. There are different kinds of handles, but mostly we care about file handles. So because I opened a file from vimlib path location, apparently this process also holds a handle to that particular directory. That's what we are seeing here, c:/repo/vimlib. So basic idea is, as you experiment with this tool, you almost uncover some of the internal workings of the operating system slowly. Now, this is about handle section, and there is this GPU. If you have a GPU, and again you have a disk section where you can see the disk activity network. You can ignore this. And if it happens to be a GUI application, the Notepad 2 happens to be a GUI application, you can also see the associated windows. Again, this is the Windows operating system related concept, not equally applicable to Linux, but even the UI elements that you see on the notepad.exe are essentially some predefined components within the operating system. That's what you're seeing here. We don't need to go here right now. So like I said before, you have this parent-child relationship. So you have a parent, you have a child. Since I launched Notepad from command prompt, it goes one step indented beneath the cmd.exe. So if I launch one more, you will see one more process that gets launched. Now, every time I launch a process, obviously every process will get a new PID, new process ID. Now, by default, without me loading any file into notepad.exe, okay, I'm basically ending up with 50 MB. So this is the amount of memory that is consumed for this particular for this process. So what is this 50 MB even? Why is the system even allocating 50 MB of memory for this process? That's because when you double click this, you have got so many modules that got loaded in order to run this program. So if you kind of tend to add up some of this, you will basically get to this 50 MB. Again, take my words with a pinch of salt, because again, you would probably see 64 MB here and it doesn't add up to 50. That's because when you load this binary, you really don't have to load the entire binary at once. As you touch the code within that binary, things get fetched into the memory. So again, they do not exactly make one-to-one match, but the idea for this is it's mostly consumed by the loaded modules here. Okay. Let's see what will happen if I try to load. Let me close some of these. Let me close this and this. Okay. So all of them got deleted. Now let me pick a big file and try to load into notepad.exe. Watch what happens. Oops, let me see if I can load it like this. So I'm trying to load it. Keep an eye on this. Do you see that? So it's still loading, and then as of now, the usage of the memory jumped from 50 MB to almost like 3.36 GB. That's because the file is so huge. It's almost like 3.5 GB here. So that's why it took that hit. Okay. Now again, the program is still loading. That's why you see CPU usage. Again, one thing I forgot to mention is the CPU I have basically has like 24 cores. Okay. So if you do the math, 100% utilization by 24 cores essentially means each core can contribute to almost like 4.16% of utilization. Okay, so that's why when I think this is, let me close this and try again. So that's why when you launch it and then load this heavy file, come on. So even when something like this happen, like your system hang or anything like that, you can go here and you can terminate it. Let me do that. So both of them are terminated. Let's try one more time. So basically what I'm trying to demonstrate here is your CPU doesn't have to go to 100% usage when you have like multiple cores in your system. Let me try to open the file again. So do you see this? It goes like 4 point or something like that, but it doesn't go beyond that. The reason for that is it's a single threaded, or it's not actually using all the CPUs to load that file. It's only basically reading that file and then trying to load it into the memory. So it's just one process, one thread that is getting used. So you never ever see this going to like 100%. In fact, if you go to system, no, not this one, but you can basically see like which core is actually utilizing this and things like that. So let me, apparently it started loading already. Okay, so you can sort this column to see which process is actually taking a lot of time here and which process is actually consuming a lot of bandwidth, and then which process is taking a lot of memory here. Apparently Chrome is taking 680 MB. Okay, now if you click 3 times, you'll get the tree view again. Okay, now I want to show you another small program to demonstrate what we mean by a memory leak. So let's see. Oops. I'm just trying to write a small program here to demonstrate, because it's easy in C, so that's what I'm using here. I have my camera here. Just give me a second. Okay. Let's say let's allocate this is like 1 KB and 1 MB. Okay. I'm trying to allocate 1 MB of memory, okay, in a loop. Let me also put this. Let me put a sleep here so that it's easy for us to see what is happening. GCC leak. Okay, I compiled it and I got a binary here. So look what happens when I launch this program. Okay, so I'm trying to run here. So a.exe is launched, and for every second you see the memory bumping up 1 MB at a time. That's because I'm allocating memory in a loop with a 2-second delay in between. So if you double click this and go to performance tab, you can see the graph shooting up. So this is one way you can figure out whether there's a leak in the program or not. Okay. Now, this also gets reflected in your overall system memory usage, but again, overall system memory will shoot up very slowly because again, I'm allocating it in a tinier chunks. Obviously, if I would have fixed it properly by freeing it, then we shouldn't hit this issue. So I'm stopping it here. So the process is killed. And if I need to recompile it and then launch it. Now, because I fixed the memory leak, I don't see the memory jumping up. Okay, this is what we mean by a memory leak. And let's also try and see, how sometimes you tend to see your laptop becoming very sluggish. The reason for that is you just have to launch your system informer and then see who is actually consuming the highest CPU usage in the column. Okay, by doing so you can clearly figure out what process is causing, and you probably can kill it. Now let's try to simulate that. For this you really don't need anything. All you need is simply perform a while loop. So if I do this, CPU.c. Okay, let me compile it. Look what happens. The CPU usage almost got to its fullest utilization. This being only single thread, as in like only one execution flow, you are seeing only one CPU getting used, and that CPU got almost used like its fullest usage. Like I said, since we have like 24 cores, the overall system usage gets divided by 24, which like I showed you will be like a 4.16 or something like that. So we are almost hitting that mark. Again, this being only a single threaded thing. So if I go to complete system overview, you would see, where is it? Just a second. I think Chrome is actually dominating here. But again, if you see here, a.exe is taking so much of time in running it. So I don't know whether you can see it. Like again, K in the tooltip, K means kernel time, U means user time. So this being just a simple while loop, there is nothing that you really that there is nothing that the operating system is actually doing it. That's why you see a lot of usage happening, a lot of percentage of usage happening only in the U side, U:60, 70, something like that. K is almost very small compared to U. Okay, because I'm not actually doing anything that requires my system, the operating system help here. All I'm doing is running some computation here. Okay, so you can essentially see that here. let's ignore this. If I launch another process, okay, same binary. If I launch it again, let me launch it in another terminal. So what you're seeing here is I launched 2 of them. Now, if you go to overall CPU utilization, the utilization has jumped from it jumped to 22. Now, if I launch one more, just look at the overall CPU utilization, like system-wide CPU utilization. Basically, what I'm trying to do here is launch multiple instances of it. So it jumped to another 4.16%. So so you're seeing increased utilization. Now, operating systems generally what they do is they spread this load, this entire load, into all the CPUs. That's why when I clicked the CPU usage, you don't see one CPU getting heavily used. The usage gets, because like I said, operating system, whenever it gets the timer interrupt, it will schedule, because there are like a bunch of processes running in the system. This a.exe, sometimes it runs on core 0, sometimes it runs on core 10, or maybe core 15, something like that. So the execution will be mapped to multiple cores depending upon what the OS thinks is more appropriate. But you can right click on this process, and there is this thing called affinity. This is again a OS Windows concept where you can tag a program to run specifically on one core, on a specific core. So look what happens when I do that. So right now, core 0 is not so overloaded. It's overloaded but not so overloaded. Now look what happens when I tag this process to only run on core 0. So if I run on core 0 and then click OK, watch what happens. Immediately the program is completely affiliated to core 0. So you're seeing like complete usage on core 0. You see that? So basically you see like 100% utilization here. Now, if I switch this to some other core, essentially, let's say core 1, what you would see is there's a drop in here, and then core 1 gets spiked up. So all we are trying to, all the operating system is doing here is it is giving us these primitives that programs can use to appropriately schedule or appropriately tag programs to run on different cores. Essentially, it is giving us a way to utilize the resources as much as we can. Okay. In fact, there are a bunch of other options here. I haven't gone through them. So you can terminate them just by clicking this. If I terminate this, that will be killed. And then you can suspend it. So if I suspend it, essentially the CPU usage will go to 0. So you don't, it's basically stopping it. It's not recommended to do on every program, but if you see some process is taking a lot of time, you can right click and then suspend it, and you can resume it as well. Freeze is slightly different. We don't have to care much about it, but in fact, when you're studying your operating system course, you see something like priority levels, like what is a you can change the priorities. So you're asking the OS to give this specific program more chance to run compared to other programs in the system when you set it to real time, something like that. Again, this priority is for computation, not for IO. IO as in you're not waiting for some inputs or anything like that. It's more of, let's say you're doing heavy calculation. When you do heavy calculations, you don't need any inputs, right? You're crunching some numbers, right? So that we call it as basically we say that IO in the normal priority. Now we have something called as IO priority, which is basically about how to deal with when the process is taking too much inputs, or when it is putting a lot of output like that. So IO priority is meant for that. Again, these are all options that you can try. Like I said, opening this will you can navigate through a bunch of options. I also want to explain the concept of thread. Why do we need threads, right? So I don't know whether this is my favorite example whenever I have to explain what a thread is. I don't know whether you used the snake game, something like snake game mobile. So most of you are familiar with this snake game, right? So there is a stuff, and the snake will be moving, and then you need to basically, the snake should eat that whatever is there. Now, if you have to program this, right, there are two things here. One, irrespective of what you do, the snake should be moving, right? Which means you will have piece of code which will dictate the direction of the snake, be it like you move from x comma y, like you move from one location to another, something like that. So there is a piece of code which keeps running in order to keep the snake moving. Okay. And the other thing is, you also want some other code to wait for user input, right? When I click left, the snake should go left. When I click right, the snake should go right, which means there is another piece of code which will basically try to take input from the user and then act accordingly. Now, the problem here is, I cannot put a input taking routine, be it read line or scanf or whatever, in the middle of where I'm setting my position of the snake, right? If I do that, my snake will not move, because every scanf or every read line will stop the execution. Does it make sense? So basically, we need two different independent executions, one for moving the snake and one for basically basically to request input from the user. So if you think about it, this is very good example for you to have like a program which needs like two independent executions. So this is where the concept of thread comes into picture, right? So what you do is, again, I don't want to go into the details here, but what you do is, in one thread, you write code, you write function which eventually make the snake move, and in another thread you try to take input from the user, be it left, right, top, bottom. Once you get the input, again, that piece of code will be sitting in a while loop. So the idea of that second thread is to always take inputs repeatedly, because you can, at any point in time, you can click left, right, up, down. Okay. So that will take the input from the user and appropriately set a global variable or something like that. And now this thread one will read that global variable and then accordingly set the position of the snake. Does it make sense? So this, again, I'm giving you a very simplistic example, but the idea is like uh, having one process with only one thread does not work for all the scenarios. And this is one prime example that will illustrate like why do we even need threads. Okay. So that's why, of course, these days, like you don't find processes with single thread. You always find process with multiple threads. In fact, even a simple notepad will have like bunch of multiple processes. So if I try to launch notepad 2 and then go to process system informer, and then and this is another use case I forgot to mention. Sorry, I'm being jumping here back and forth, but bear with me. So there are these two very important icons. I did launch notepad2.exe, but I do not know where the process for this notepad2 is. Okay, so what you can do is you can click this icon, and the cursor will become like a plus sign, and you can drag it and then put it here. Now it will automatically highlight the process for that program. Okay, so Again, coming back, when you double click that, you will go to this threads tab. You will see like there are like how many threads? There are like 7 threads that are created for this specific program. Okay. This is how you can see what threads are there within a process. Okay. Without a process, you cannot find a thread. So threads have to be part of the process. Now, every process will have, every thread will have its own sequence of functions, right? Like I said, in our snake game example, the first thread would be calling a function called move snake some x comma y. That move snake function could be calling some other internal function, or that function could be calling some other internal function. So this is what we mean by call stack: one call going into another call and another call. So essentially a call stack relates to a thread. That's why when I double clicked a thread, what you get is called as a call stack. So in this example, RTL user thread start called this one and this one and this one and this one. You read it from the bottom, basically. Okay, does it make sense? Now, if you refresh it, apparently this is a waiting function, so you don't see much happening. But basically, this call stack is intended to change, because as the program executes, as the thread executes, you complete the function and then you go back to its caller, right? So you can come across this. Now, one important point I even completely forgot to mention here is there is this concept of user mode and kernel mode, right? Operating system will always run in kernel mode, just because kernel mode is more high privileged mode. When I say mode, it's not very special to the operating system. It's a mode very special to the CPU. So what that means is when you run code in user mode, the CPU is restricted to do only certain operations. And when you run code in kernel mode, the CPU is not restricted in any way, and it can do anything that it wants. So because the operating system is the main program which has to manage the entire resources, it will basically always run in kernel mode. So that's why you see this distinction. All of this yellow color that you see is in user mode, and all of the entos kernel.exe is part of this is the user mode part and this is the kernel mode part. Okay. So again, I'll just go back to the slides for a second. I wanted to just show you how the process memory look like. So in a given system, basically you will have uh, 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 what we work with is called virtual address space, meaning you don't really need the one which I showed my laptop device. It has only 4 GB of RAM. But the good thing about operating system is it doesn't limit you to 4 GB. You can write programs thinking that you have like infinite memory. The reason why we are able to write that programs is behind the scenes, operating system will manage your memory as if you have like infinite resource. Not only that, every process will have this map called memory map. We call this like address space layout is what we call it as. So if you see here, from starting with 0 to almost like 2 GB, it's user mode. So all the code that you have will lie within it. That's why if you see any of the process, again, I'm showing you the x86 version. In fact, we should look at x64 because my system happens to be x64. So you will have a lot more space for user mode. So here what you're seeing is you have like almost 128 TB of memory for you to play with in user mode, and another 128 TB of memory allocated to the kernel mode. Again, this is virtual. You don't really need to have that much of RAM in your system, but this is how a programmer will imagine his system memory is. Now, that's also the reason why when I open any modules, you would see, just give me a second. So all the threads that you see here, these will fall below this 700, 7FF mark below. below that, because all of this is basically user mode part of the process. Now, this is from a.exe. If I try to open system, which is basically the operating system, and then look at its memory modules, look what how it will look like. Look at this. These modules basically has a base address of FFF, which means it is on the upper portion of the virtual address space. Okay. Again, concept which is very much discussed in the books, but what they mean is operating system will always run in kernel mode, and user mode, user code, or all our programs run in user mode. Whenever we need to access a resource, we make calls into the operating system, and we get the job done by the operating system, and we again continue with our own work. Okay, so this is one major distinction. Don't stick to the definitions too much, because they don't really make a lot of sense. All we need to care when you are looking through or studying operating system is basically to understand what we mean by kernel mode and what we mean by user mode. Again, it's not something that we can cover in one session, but I'll give you very good references which you can go look at to get further more understanding. Now, as I said, this is all virtual. Like, I really don't have like 128 GB of 128 TB of RAM, right? So now this virtual view of the system has to be somehow mapped into the real RAM, which is just 4 GB that I have. Now, that's where the virtual to physical address translation come into picture. This is done by memory manager. Again, we are not going to discuss any details here, but given a virtual address, be it any virtual address, like this is a virtual address because this is not real. I don't have like 128 TB of RAM sitting in my machine, right? This is a virtual address, or anything that you see on your system is a virtual address. It's not physical. Okay, in order to really look at physical address, you need a debugger to in fact debug the kernel to see what the physical addresses are looking like. So whatever you see here, everything is virtual address. Now, the component within the OS, which we call memory manager, will perform these address translations. In fact, it doesn't do the actual address translation, because the actual address translation will be done by the CPU itself, but the memory manager will set up the structures required to facilitate the CPU to do the translations. Okay, so this is a 32-bit. If you're using older machines like Intel older machines, we call it as x86 or 32-bit architecture. There you have this sort of a mechanism. You break the 32-bit address into a bunch of tables, and then you try to eventually map into your RAM. Okay, but on a 64-bit machine, it's slightly little different again, but the point is very similar. On a 64-bit machine, you have like 47 bits, so not 64. Because of some limitations. So those 47 bits basically will be broken down and then again mapped into ultimately into the limited physical memory that I have. Okay, so again, OS basically gives you all of these freedom, as well as these unlimited resources for the programs to play with. So we never think how much RAM we have. We simply write code in your Python or your Java or your C, and ultimately the OS will does this complex job to realize that or execute that program by the CPU. Okay, and I'll stop here, and these are the references. Again, like I said, most of the books that you refer does not the course related, the university related books, they don't talk these details, and most of the stuff is doesn't make any sense. So I highly recommend these books if you want to really understand be it Linux or be it Windows. These will really help you understand what I just spoke about, and try to use this tool as much as you can. It will really enhance your understanding. One last thing that I want to show you, which is sometimes what happens is let me go here. Let me terminate. Again, you can filter, you can search here to find the processes by name. I'm just terminating all the a.exes. Okay. And then you can clear this. Now, what I'm trying to do here is I'm trying to delete this directory. Okay. When you try to delete something, you always tend to get this dialog. Somebody is using this and I am unable to delete it. Okay. You won't be able to know who is using it, right? So all you have to do is find handles. Like I said, handles is basically another word for all the resources a process use. So what I'm trying to do here is when I click this button, I get this pop-up where you can search for files, because that's what I'm trying to delete. So file, and then search for temp. I should have named that folder a little better to get the filtering much easier. But anyway, let me redo this example in a different, so that it illustrates the purpose. Let's say I have okay, I'll create this folder, and then I'm navigating it, and I did whatever I want here, and then suddenly I came here and I wanted to delete it. When I try to delete this, the folder does not delete. Okay. Now what I will do is basically, because the folder is not getting deleted, go to the file handles and filter it with the file, and then find it. Now what this tells me is basically it is showing me that cmd.exe with this process ID is actually using this directory. And this is the handle ID, which we don't have to care. You can right click to it and go to the owning process. Now, when I do that, it will take me to the process. Now, what is actually happening here is apparently I moved into this directory, because of which CMD is holding that particular directory. Okay. So if I move back and then if I try to find again, you won't find it. And now if you try to delete it, you can happily delete it. So there are these things. Essentially, it's all about resources, how the system is utilizing them, and you can basically leverage this tool to find that. Hope I think it made a little bit of sense of how your systems work and how you can take advantage of this tool to understand and dig deeper. There are like so many columns that you can play with. Like I only touched the surface, so you can look at bunch of parameters. You can add them, and then you can see you will get a lot of columns here, and you can investigate more. Unfortunately, these days uh, nobody is actually interested in these system level things, just because AI is the name of the game. So but if you are really interested in these sort of things, I would highly encourage you to go through these references, which will not only become experts in these kind of topics, but also make you a better developer or a programmer. Okay. So as usual, here are the references. You can always reach out to me for any questions. Questions are always welcome, how dumb they are. Okay, I'll stop it here. Let me know if you guys have any questions. I'll take a pause for a minute, and then we can call it done.
Sir,
Yeah.
we're having a question, sir.
Sorry, Karthikeya, I cannot hear you.
We are having some questions, sir.
Sure. Yeah.
why and what happens during system hang?
So basically, there are multiple things to it, Karthikeya. So when a system, who asked it?
Students, sir.
Okay, anyway, I think anyway, so basically when a system hangs, there are multiple levels to it. It sometimes what happens is it could hang in the kernel itself, which means the system completely gets freezed, so you won't be able to do anything. In that case, what could have potentially happened is you would end up in a deadlock. Again, I didn't get a chance to discuss all these concepts, but the idea is like OS is waiting for some resource, or multiple processes are waiting for the same resource. So it depends upon the situation. So when such a hang happens, what we do is something called as we take memory dump. If you go to Windows documentation, you will find it, how to take a memory dump. Again, unfortunately, when a system hangs, you cannot go into the system and then take a dump. You need to externally connect a debugger to it and then take a dump out of it. Now what we do is we take the dump, and then we take the dump into a different machine, and we try to analyze it using the debugger tools, and then only we will be able to pinpoint what is happening. What the again The beauty there is, again, by the debugger, debugger is nothing fancy. It's just another version of system informer, so to speak. But what it will do is it will show you the list of processes and their state, and looking at the processes and then their threads and then their call stacks, we will clearly know why a process hang, or why a system is taking heavy usage and things like that. Again, it depends upon the scenario.
Okay, sir. Okay, sir.
Anything else?
No, sir.
Okay, yeah, thank you guys. I think always feel free to ping me or reach out to me if you have any questions. We have Edgroom, the forum that is created, I mean the webinar page, discussions page that is created. You can post there, or also you can reach me with any other channels that you are comfortable with. Yeah, thank you so much.